Hello everyone, this is Dhanalakshmi, Assistant Professor from EEE Department of RMT Engineering College. In this session, I would like to discuss about Hurwitz Criterion, which is a very important technique to find the stability of a system. So in control systems, where our unit 4 is all about stability and compensator design. So in order to find the stability of a system, where we have to first locate the roots. We want to find out where the roots are lying in the S-plane, and based on that we can comment on the stability of the system. So in that case, for the stability of the system, here I've taken Hurwitz criterion. So in this session we will discuss about Hurwitz criterion. So before proceeding with the Hurwitz criterion, so first let me tell you how the on basis of the location of poles, how it is going to affect the stability of a system. So based on the location of poles, like whether the poles are lying on roots are lying on the left half of the S-plane or right half of the S-plane, or whether it is on the imaginary axis. So based on all these factors, it is going to tell us the stability of the system. So here you can see that in the first one second, and let me zoom in. Okay, so here you can see that when my root, that is when the root is lying on the left half of the S-plane. Go to the slideshow. I think it will be better. Okay, stop sharing and stop putting slideshow. Okay, so here you can see that when my root is lying on the left half of the S-plane. So here we can see that when the root is lying on the left half of the S-plane, where the impulse response of the system, right? So the impulse response of the system is exponentially decaying, where you can see that. So therefore the system is stable because it is exponentially decaying, and it is not moving towards infinity. The system becomes stable here. Whereas in case of the second factor, where my root is lying on the right half of the S-plane. So here we can see that the root A is lying on the right half of RHS of the S-plane. So in that case, the impulse response is exponentially increasing. So here we can see that it is exponentially increasing, which means that the system becomes unstable, where it is keep on exponentially increasing, it is moving towards infinity. So therefore, we can say that the system is unstable. And whereas the other case where we have complex conjugate roots, instead of the real roots, if the roots are complex conjugate, then in the same way, the conjugate pairs, when they are lying on the left LHS of the S-plane, that is left half of the S-plane, again, you can see that the system is the impulse response. The impulse response of the system is damped oscillatory, where the oscillations are damping out. So therefore, the system becomes stable because you can see that the oscillations are getting damped here. So at one point, it becomes the oscillations will become zero. So therefore, we can say that the system is stable system. So this will happen when the complex roots or the conjugate pairs are lying on the left half of the S-plane, LHS of the S-plane. Whereas similarly, the other way, that is when the complex conjugate pairs are lying on the right half of the S-plane, that is RHS of the S-plane. Here you can see that the roots are lying on the RHS of the S-plane. In that case, you can see the oscillations are increasing. Impulse response is exponentially increasing. It's an oscillation where oscillations are exponentially increasing, which means that the system becomes unstable here, right? So since it is oscillations are not damping out, here it becomes it's increasing, exponentially increasing, which leads to an unstable system. So this is another way. Where the other possibilities, when my roots are lying on the imaginary axis, this is something cat on the wall, where it might go to stable state or it might become unstable also, based on the movement of the pair of roots. Whether if it moves towards the left half of the S-plane, the system oscillations will be damped out and oscillations will get reduced, the system will become stable. If the same roots, if they're going to move towards the right side, then oscillations will become exponentially increasing, which means that the system will become unstable. Since now it is the single pair of roots which is lying in the imaginary axis, which makes the system to become marginally stable. Marginally stable is something called limitedly stable. The stability is over on the margin. That is, either they can become stable or unstable based on the movement of a pair. So right, so far if the roots are lying on imaginary axis, they are oscillatory. System is oscillatory, which means that it is marginally stable. And the same way, instead of having one pair of conjugate, if the two pairs, a double pair of roots are lying on imaginary axis, then obviously the system will become unstable, because here you can see that the oscillations are linearly increasing. So therefore, again, obviously it leads to unstable system. And here, if a single root at origin, if I have only one root lying at origin, then my system impulse response is a constant here. The impulse response is constant. So constant, but at any point of time, it can be increasing or decreasing based on the movement of the root on the LHS or the RHS side. So therefore, it is again, we said it as, we will be saying this as marginally stable system. Right. Now we'll go on to the Routh-Hurwitz criterion. So when we take Routh-Hurwitz criterion, that is RH criterion, we have three category of stable system, we say. One is called the stable system, the other one is called marginally stable system, the third one is unstable system. So we know that when all the roots of the characteristic equation, when they lie on the left half of the S-plane, right, then we say that system is said to be then the system is said to be stable system. If they lie on the right half of the S-plane, then the system is said to be unstable system. If they lie on the imaginary axis, then we say that system to be marginally stable. So this is the three criteria we have in Routh-Hurwitz criterion. So in Routh-Hurwitz criterion, if all my roots are lying on the left half of the S-plane, then the system is said to be stable system. Even if one root goes on the right side, if one root is lying on the right half of the S-plane, then the system is said to be unstable system. And if the roots are lying on the margin, that is if the roots are lying on the imaginary axis, then the system is said to be marginally stable or limitedly stable. Right, so we'll see the thing now. For in case of finding the stability or to comment on the stability of a system, first we have to construct the Routh array, and after this forming the Routh array, we can comment on the stability by just observing the first column of the Routh array, RH array. So once we complete the RH array, we have to observe the first column of RH array, and we have to check whether there is any sign changes are there. If there are sign changes, we have to check the number of sign changes are there, and that many number of roots are lying on the RHS of the S-plane. So that will lead you to the unstable system. If there are no sign changes, which means that all the roots are lying on the left half of the S-plane, so therefore the system is stable. Right. So we'll see how to construct the Routh array, and then from the array, how to comment the stability of a system. So here we can see that if a characteristic equation is given, so we have to get the characteristic equation. We all know that in order to get the characteristic equation of a system, we have to first find out the transfer function of the system. Once we know the transfer function of the system, the denominator polynomial of the transfer function will become the characteristic equation. So we have to take the denominator polynomial of the transfer function, and we have to equate it to 0. That will give us the characteristic equation of that system. Right? Once you know the characteristic equation, say for example, if a characteristic equation is like this: a naught s power n plus a1 s power n minus 1 plus a2 s power n minus 2, it goes on up to sa power n, an equals to 0. So if this is a characteristic equation given, then you have to form two rows here. So the s power n row you have to form, then s power n minus 1 row. For example, if the highest power of s is 5, then I have to form s power 5 row, and subsequent row will be s power 4 row. Right, so I have to form the s power 5 row and s power 4 row from the coefficients, which is from the coefficients of the characteristic equation. So what you have to do, so for s power n row, what I have to do, I have to take the odd coefficient. Depends upon this n, whether this n is going to be odd or even. I have to form the odd row or even row, just taking the coefficients of that particular term. Right, for example, if s power n row I'm going to take, then I have to take the a naught is the coefficient of the s power n term. So I'll be writing a naught, then the next term will be a2, then a4, like that it goes on. Similarly, the next row will be s power n minus 1 row. So s power n minus 1 row, here the coefficient is a1, the next term will be a3, a5, like that it goes on. Right. So if you are what we have to do is the first two rows, right? The first two rows which we are framing from the characteristic equation is like this. It would be like this, right? So from the characteristic equation, we have to frame the first two rows, s power n row and then s power n minus 1 row. And after that, below that, you have to form the subsequent rows. Thus, those rows you can form it by the formula. By the formula, you can use a formula to form to frame that to frame those rows, right? For example, if the S power n minus and this A0, A1, A2, A3 is the first row, then B0, B1, B2, B3 is the second row, which these two rows we are forming from the characteristic equation. So we are taking the coefficients of the characteristic equation and then we are forming like this. Now, in order to find the next subsequent row, that is S power n minus x minus 2, that is next subsequent row, what we have to do, that is the elements, let us assume that the elements are C0, C1, C2, C3. Right, in order to find the C0 value, what I have to do is I have to multiply B0 into A1, this into this, B0 into A1 minus A0 into B1, this into this divided by B0. So this is the formula given. So where you can see that from the matrix we got this formula. That is, here you can see that B0 A1 minus A0 B1 divided by A0. Okay. So here you can see that B0 A1 minus A0 B1 divided by B0. That is, I have to get the formula. I have to use this formula. That is B0 into A1, then A1 into A0 into B1. That is A0 B0 into A1 minus B1 into A0 divided by B0. So this will be my formula. Right, I'll repeat once again. So in order to get the C0, right, in order to get the C0, what I have to do, I have to multiply B0 into A1, then I have to multiply minus B1 into A0 divided by this element, B0 element, right? This is how I have to use the formula in order to get the C0 component, that is C0 element, right? Now the same way I have to do it for C1 also. In order to get C1, I have to use it the same way. So here I have to take the first column and the third column, right? And the third column I have to take, right? And take the third column. So in order to find my C1, that is here the same way, B0 into A2 minus B2 into A0 divided by B0. Is that clear? So here you can see that B0 into A2 minus A0 into B2 divided by B0. So this is how we have to find out the elements C0, C1, C2. Like this, I have to complete this row. Right, so the same way we have to do it for the subsequent rows, right? So this is the formula to fill up the Routh array, right? Then after this, what I have to do? One second. Erase all these things. Let me erase all these things. Right. So the next is we'll have to check what are all the things we have here, right? Okay. Now, in this Routh array we have 3 cases here, right? So the 3 cases are, one is the non-zero element, all zero row, and first element in a row is 0. That is, a non-zero element is nothing like a normal Routh array. It is like a normal Routh array where no zero elements will be occurring, right? Whereas the second case is all zero row. All zero row is the one where in one particular row alone, the entire row will become 0. That is all zero row. Right, so the all zero row is something where one particular row becomes, the entire row will become 0. That is all zero row category. And the third one is nothing but in a row, the first element alone is 0. That is going to be first element in a row is 0. So in these 3 cases, we'll check how to complete the Routh array. And after completing the Routh array, how to find out or how to comment on the stability of the system. So here we can see that I've taken a problem here. So this is the characteristic equation given, and we know how to, this is the characteristic equation given, and we know how to form the first row, right? This is the characteristic equation given, s power 4, 8s cube plus 18s square, 16s plus 5 equals to 0. Now the highest power of s is 4, so therefore I have to form the s power 4 row. However, for forming s power 4 row, I have to take the coefficient of even terms, right? So since 4 is an even number, so I have to take the coefficients of even terms. So for s power 4, the coefficient is 1, and the next even term is s square term, and that coefficient is 80, and the next even term is constant term, which is the 5. So therefore, I have taken 1, 18, and 5 for filling up the s power 4 row. Now I have to take the second row, that is s cube row. That is the next subsequent row will be s cube row. In order to find the s cube row, again I have to take the s cube coefficient. The coefficient of s cube here is 8, right? So I will be taking 8 as the 8 is a coefficient for s cube I have taken here. Now for the next odd term, s cube is an odd term. So the next odd term will be s term. So that is 16s. So therefore I'm taking 16, the coefficient of s term, which is 16. right? Now you can see that in the S cube row, there's a common divider available. So therefore I can simplify this row. I can simplify this row. That is, I can divide this row. I can divide this row. I can divide this row by 2 because there is a common divisible available, right? So therefore after dividing, you can divide by 2, or even I can divide this row by 8 also, because 8 is a common divisor for that row. So what I'm doing, if I'm just multiplying or dividing by 8, right? If I'm just dividing this equation, not equation, this row by 8, then this row will become 1 and 2, because 8 by 8 will become 1, 16 by 8 will become 2. Right now, again, I'm writing the same S3 row alone, right? I'm not changing the row, just simplifying the S3 row, and I'm writing it as 1 and 2. Yeah, instead of 8 and 16, after simplifying it will become 1 and 2, right? Now in order to get a square row, right, now the thing is we have to form this square row. In order to form the square row, we know that how to get it, right? So this into this element into this element, so 1 into 18 minus 2 into 1, right? 1 into 18 minus 2 into 1 divided by 1. So that gives you 16. Is that clear? So 1 into 18 minus 2 into 1 divided by 1. So that gives you 16. The same way we have to find out for the next element. Now 1 into 5, right, minus this into here. We don't have any element, so we have to assume that as 0. So 1 into 5 minus 0 into 1 divided by 1. So that gives you 5. Right. So this is how we are completing the square row. Same way we have to do it for S1 and S5 also. For S1 again, for getting this element, this 16 into 2 minus 5 into 1 divided by 16, like that you have to do it. You have to complete the array, right? So using this formula, we can complete the array. And once we complete the array, now we have to check, we have to take the first column of the Routh array, right? We are going to take the first column of the Routh array. And after taking the, I'll clear this one. Right, first column of the Routh array, and we have to check whether there is any sign change. We have to go and check whether there is any sign change. When we check here in this problem, there's no sign change at all, because all are positive elements, there's no sign change. So since there are no sign change, right, so it is observed that all the elements are positive and there is no sign change, the system is stable. Right, so here the number of roots are the highest power of S is 4, which means that there are 4 roots, right? So all the 4 roots are lying on the left half of the S plane. So therefore we can say that the system is stable. So this is the first category where the Routh array is a normal Routh array, no 0 elements are available, right? Right, now we'll go to the second problem, the second category, where you can see that in this category, we have a row, a complete row becomes 0. That is S3 row. This complete S3 row becomes 0. This is another category. Right? When we have a row, an entire row becomes 0. This comes under all 0 row category. All 0 row. Right? That is all 0. A row completely consists of all zeros. Right? So in that case, what you have to do, we cannot proceed. We cannot proceed if an entire row becomes 0. We cannot proceed the subsequent rows. We cannot do S square, S power 1, S power 0 row. In that case, what you have to do is you have to take the previous row. Right? You have to take, if S power 3 row is the all 0 row, then I have to take S power 4 row. Then by taking S power 4 row as an auxiliary equation. So what I have to do, since my S3 row is a all 0 row, I have to take the previous row. So my previous row is S power 4 row. So I'm just taking this S power 4 row here as my auxiliary equation. Right? So S power 4 row in the sense S power 4 plus 6S square plus 8. Just frame this as equation. S power 4 row, you just take it and frame this as equation. This becomes your auxiliary equation. Now what I have to do, I have to differentiate this auxiliary equation and I have to substitute again as my S3 row. Right? So whenever I have all 0 row occurs, then what I have to do, I have to take the previous row and that row as an auxiliary equation. I have to differentiate that auxiliary equation and then I have to substitute it as my all 0 row. Right, my all 0 row here is S3. So for substituting for the elements of S3, what I have to do, I have to take that auxiliary equation and I'm going to differentiate that. And after differentiating, I'm going to substitute here. If you differentiate this one, S power 4 plus 6S square plus 8, if you differentiate, it will become 4S cube, right? So it will become 4S cube, then 4S cube plus 6 into 2, it will become 12, right? So 4S cube, 12S square, right? Sorry, 12S, 12S, right? Okay, 4S cube plus 12S equals to 0. So when you differentiate it, when you differentiate this expression, it will become 4S cube plus 12S. So therefore, in the place of 12S cube, what I have to substitute here, I have to substitute it as 4. and here I have to substitute it as 12. But again, this 4 and 12, you can simplify that row, because that row you can divide it by 4. 4, 12 is a 4, 12. 4 is a common divisor. So therefore, what you can do is you can simplify this row. So if you divide it by 4, this row will become 1 and 3. 4 by 4 is 1, 12 by 4 is 3. Is that clear? So whenever all zero row comes, what we have to do is we have to take the previous row, and that we have to consider it, we have to make it as an auxiliary equation. And taking that auxiliary equation, we have to differentiate that auxiliary equation, and we have to substitute it as S3 row. That is the row which becomes all zero. Right now, again, we have to proceed as similar. That is similarly as like the previous problem, we have to construct this array, and again we have to check whether any sign changes are available. If there is a sign change which indicates that that many number of roots are lying on the right half of the S-plane, which will make the system to become unstable. If all that there is no sign change, obviously then all the roots are lying on the left half of the S-plane. So therefore, we can say that the system is a stable system. Is that clear? So you can see here, one second. So in this problem, yes, in this problem, you can see that after completing, and from that auxiliary equation, we can find out the roots. So here we can see that since that all zero row comes, which means that this auxiliary equation, one second. From this auxiliary equation, we are totally getting 4 roots, and all if you check, all these 4 roots are lying on the imaginary axis, which means that the system is marginally stable. Whenever the roots are lying on the imaginary axis, then we can say the system is said to be marginally stable. And the third category, where one element of a row, not one element, the first element of a row alone is 0. In that case, in a row, if the first element alone is 0, then this is the category. In that case, what we have to do is that element alone, instead of taking that as 0, you can take that as a small value del. Right? Keeping instead of 0, we can letting that del value to be 0. That is, instead of taking that term to be 0, we are making it as a small value as del. So if we are proceeding as such, as similar, we have to complete the Routh array with the instead of 0, we have to keep the del value. And after completing the array, now we have to rewrite the array. When you rewrite, now in the case of wherever you have del, you replace all the del by 0. Right? So this is the third category. Again, after completing the array, we have to check whether there is any sign change. So here you can see that there is a sign change from positive to negative, which means that the 2 roots. Here you can see that from positive to negative, one sign change is there. That is, I want to continue. So here you can see that from positive to negative, one sign change is there. Again, from negative to positive, again there is another sign change. So totally two sign changes are available, right? 2 sign changes are there, which indicates that the 2 roots are lying on the right half of the S-plane. Even one root, if it goes on the right half of the S-plane, then the system will become unstable. So therefore, we can say that the system is unstable. Oh. Okay. So this is another problem where you can where you have more number of sign changes available. Thank you all.